Example 6. Okay, so now we're going to do the same thing. So here we're given this matrix S. We have pi 1, 0, 3. Okay, again, here, just so you know, not to get confused, this is not a mapping, this is the number pi. Okay, so now, if we have this matrix, now, here's, from the previous video, we can jump right in to find the eigenvalues for this vector, this matrix, because this matrix represents a mapping, right? So we can find the eigenvalues that are for this matrix just by going right to the equation, because now we have an equation that we set up, which was what? We set up that equation equal to 0, right? So now all I have to do is I've got this matrix, and then of course what do? Once we found this, then we found the determinant, and we use the determinant to find out when is it equal to 0, and then by that we found the eigenvalues. So all we're doing is we're jumping ahead, and now we know how to set this up. So we know that this is just going to give us the minus x down the diagonal, right? So to find this, it's just basically subtracting x along the diagonal. That's what it amounts to. So now that we know that, we can jump down from here to finding this, which is going to give us this, and then we're going to set up the determinant, right? We're going to find the determinant, the form of the determinant, and we're going to find out when is it equal to 0. And so that's what I did. So we went from here to here to here, and now we have to solve. Now again, the zero product principle tells us, hey, this is only going to be equal to 0 when x is equal to pi or when x is equal to 3, and therefore we have our two eigenvalues. So lambda 1 is equal to pi and lambda 2 is equal to 3. It's that easy. Okay, once we know the concepts and we understand what's going on in the background, the theory, and then once we introduce the techniques, now the techniques make more sense because we know what's going on. Okay, so now to find the associated eigenvectors, what we're going to do is we're going to do what we did before. We're going to plug in the lambdas and solve for x. Or excuse me, we're going to plug in for x and then solve for our zeta or z vector. Okay, so let's set that up. So again, if I set this up, what am I going to get? I'm going to get, well, let's do the first one, pi. So what are we going to get? We're going to get pi minus pi, 1, 0, oops. Three minus pi. Now the cool thing is since it's a 2 by 2 matrix, just not to digress, but since this is a 2 by 2 matrix, we should know how to go from here to here really easy. Okay, using the determinant formula that we've learned. Okay, so now, so here we've got this times our zeta. Right? And again, I'm going to let you solve this, but this is going to give us, oops, equal to what? 0, 0. Oh no, not 0, 0. A 0, that's what I meant. And of course, A cannot be 0, obviously. Now, then once we have that one, now we could do the same thing by plugging in lambda 2, which is 3. So all I'm going to do is I'm going to go back here. I wouldn't do this. You could write yours on your notebook, but I'm just going to do this. And I'm going to go through the same process. And again, this is pretty easy to solve. And in this case here, I get this. I get this. And again, b is not equal to 0. So now we got a technique that, given a matrix or given a representation, a map, we can now find the eigenvalues for that map and the associated eigenvectors using this technique. Okay, have a great day.